Okay, so here we go with the temperature. Now, as I mentioned in class, temperature can be a significant contributor to deformations. Sometimes it is a negative thing. Sometimes it can be used, the fact that you can produce deformations with temperature can be used as a positive thing because you can make things move by heating them without having to push. That can be quite effective. So, first, let's remember that when we calculate delta or theta, we say it's the integral of m1. Now, thus far in the examples we've been using mp over ei, but what that really is, and as I presented in the initial derivation, that is just the curvature due to the actions that are producing the deformation. Now it turns out, plus, when we write the shear contribution is V1, and we normally write VP over AVG, but that's really just, more generally, is just the strains due to the shear, ds. And finally, we have N1, but it's not NP over AE, but in general the strains due to axial ds. I may have used in the past maybe a different notation here like EV. It doesn't matter. This is strains due to shear, right? Now, if we have temperature as the loading, then what we have is we're going to treat the simplified version where the temperature distribution across the cross-section of our element is linear. So if we have our cross-section, actually let me be a little bit more generic, not make it rectangular necessarily. Let's say that we have a cross-section. This is the centroid, and these are the principal axes. Okay, let's say that we are interested only in one direction of things, so this is h bar, which is the height of the section. This is the full width. Now, if we heat the top of the section by an amount delta T at the top, then that multiplied by a coefficient alpha, which is known as the coefficient of thermal expansion, gives us the strains that we get there due to that increase in temperature. So the strains look like this. The strains at the bottom could be delta T, the change in the temperature at the bottom, times alpha. So that's the strains in the bottom. These are the strains. So temperature produces strains just like loads. And of course we are talking about from a reference, right? So we have to say right now whatever is going on is the reference, is 0. Now from this moment on I change the temperature by this much, what happens? So from having a reference, we say my temperature on the top of the section increased by delta T at the top times alpha, and my temperature at the bottom of the section increased by delta T at the bottom times alpha. As I said, we will use the assumption, doesn't have to be true in reality, but it's often adequate, that the temperatures within the section inside are varying linearly. Now this is the neutral axis, or the axis that goes through the centroid, and so on, right? So we're assuming bending in only one direction and so on, the simplified version of things. So in this sketch, that strain is already this one. So this is EP. And this angle, that angle, is VP. So from that sketch we have this and we have this. And I can say that due to temperature, gamma V is 0. So temperature does not give us shear strains, and the curvatures and normal strains that it gives are just this very simple plot. You plot the delta T times alpha at the top, the delta T times alpha at the bottom, join them linearly, whatever is happening in the neutral axis is EP, and the angle that it forms is Vp. That's it. Okay? It's actually, now I can give you formulas if you want for what those things are, but you know, I personally would prefer to say, just draw the thing, calculate what it is. But if the distance from here to here is, let's say, y bar, so the neutral axis measured from the top is at y bar, then you can say that Vp is delta t at the top minus delta t at the bottom. Actually, this is independently of y bar divided by h bar, right? So that's the angle, because that angle is of course very small, right? So for small angles, tangent is equal to the angle, is equal to the sine, and so on. So that's what it turns out. And then EP is equal to, you can write it in several ways, but I'll write it as a linear equation starting from the bottom. So it would be delta t at the bottom times alpha plus, this thing cut off. It would be delta t times v times alpha plus what? Plus the angle Vp multiplied times the distance to there, which would be h bar minus y bar. So if you want formulas, those would be the two formulas. Okay? Really, all there is now is just apply it. Because the formula is still the same, it just gets easier, right? Because the curvature for bending, instead of requiring that you do statics for the loading, is just determined directly by the temperature on the bar, which we are assuming is constant along the bar. What else? The axial strain, which would require that you calculate statics on the loads, is just directly given by this, or by the sketch if you like, right? And then you just do the integration in the normal way. Now, a question that often students will ask at this point is, what if I have loads and temperature? The answer is, the problem that we are handling here is linear. And because it's linear, that simply means that the effect of two things is the sum of the effect of each thing. Therefore, you don't need to think in terms of what if I have temperature and loading. If you have temperature and loading, you have two problems. One with temperature, one with loading. So you solve the loading, you solve the temperature, you add them together, that's the answer. Okay? So let's try an example just to apply it, right? Let's use the same structure we've been looking at. Trying to keep this a little bit clean for you guys. Okay, so let's assume that we have what? Let's see. Let's assume that we have our structure, and that we have is, this again was 2H. 2H, I'm going to give it numbers at some point now. But I'm going to say that these bars have a cross section which are 10 inches by 20 inches. Okay, 10 inches by 20 inches. I'm going to say this is made out of concrete. And for concrete, you can go to the internet and check what is the coefficient of thermal expansion, and you will find that it is approximately 12 times 10 to the minus 6 per degree centigrade. Okay? Or if you'd like, centigrades to the minus 1. Right? In other words, you multiply this times degree centigrades, and that's your strain. Times the change in degree centigrades, and that's your strain. Right? So what we want to do is to calculate delta C in the vertical direction due to (30°) increase in temperature at the top on BC. So on bar BC, we're going to heat the top by 30° centigrades. We're going to assume that while we did that, we could keep the bottom at the ambient temperature or whatever it was before, and that the temperature is varying linearly throughout. It's obvious that this is a problem that can only be true for some time, right? Because depending on the sources and so on, there is heat flux going through the structure, and the temperatures will tend to average out and all kinds of stuff. But in the time scale of that is short, in other words, on a given minute or something, we can say that at that time, the temperature distribution on this bar was like this. And we would like to know at that time what happened to point C due to that temperature in the vertical direction. At the same time, we're assuming that there is no temperature change on AB. Okay? So, if I look at my strain diagram, I'm going to get that on the top I have 30° centigrades multiplied times 12 times 10 to the minus 6, right? And that's my strain. And that's 360 times 10 to the minus 6, or 36 times 10 to the minus 5, right? And that my strain in the bottom is 0. I also have that the distance from here to here is 20 inches, because that's the height of the bar. So you can go to the formula if you want, but I'm just going to look at it and say that my Vp, due to the loading, is just 36 times 10 to the minus 5 divided by 20. Or the same thing as 1.8, right? 1.8 times 10 to the minus 5, or 18 times 10 to the minus 4 inches to the minus 1. So that's my curvature, right? At the same time, because my cross-section is a rectangle, has a neutral axis in the middle, the centroid is over here, and so on. So I can see that my epsilon p, which is red at the neutral axis, is here, and that epsilon p is just half of this one, so that I see that it is equal to 18 times 10 to the minus 5 inches. I'm sorry, no, this one is no units. That one is inches to the minus 1. This one has no units. So 18 times 10 to the minus 5. And that's about it, right, for calculations. Now we can just simply calculate what is the deflection at C in the vertical direction, and we get delta at C in the vertical direction is equal to the integral of, over bar BC, M1. Remember, M1 was just X, right? Okay, now comes a question of sign convention. When we put the 1 kip load, and we looked at this bubble, We took M1 to be plus like that, right? Therefore, our M1 is plus when this kind of bending is taking place, right? When the bar is being bent like this, so it doesn't hold water. When the bar doesn't hold water due to the bending, it's what we chose to use M1 as being plus. Now, if we heat the bar on the top, the fibers on the top of the bar are getting longer, right? So the bar is also, due to temperature, bending so it doesn't hold water. Therefore, this curvature is of the same sign as that M1. So there is no negative here. It could have changed if you had changed the sign of this, but what you have to recognize is this is producing this kind of curvature, and this is, and therefore it is of the same sign as this, and therefore it's plus. So we have M1, which is X, and then MP over AI, which is the curvature due to the effect, is just 18 times 10 to the minus 4, right? No AI, nothing, that's the curvature. dx, and then it's from 0 to 2h, right? And so our answer is 18 times 10 to the minus 4 times x, which is x squared over 2, and x squared over 2 is 4h squared, right? So this is equal to 4 over 2 is 2, 18 is 36. So 36 times what? 10 to the minus 4 multiplied times h squared, right? Now to get an actual number, let's say that h is equal to 10 feet or 120 inches. So if you plug in 120 inches in there and you do the computation, this comes out to be 0.51 inches. So actually you get, with 30 degrees centigrades heating on the top, you get a half inch moving up on the tip of this point, right? All right. Wait a minute. Did I do anything? No, I did not do it, but I should have done it. I should have mentioned it, right? The question now is, what is the effect of the axial? Because this was just bending, right? Shear never does anything, but what about the axial? Well, the axial doesn't do anything because even though there is an EP, what is 0? N1, right? So N1 times something, dx, but the N1 is 0, as we've shown before, and therefore, over here, right? So there is no bending contribution in this case. That's everything. Now, to conclude the lecture, let's finish it as follows. Let's say that you want to calculate the temperature change that you have to put in AB such that with the temperature that we got here, point C will not move. I repeat. I want to calculate how to heat bar AB. I want to know how to heat bar AB such that point C doesn't move. I'm assuming at this time that the temperature on BC, which is what we looked up here, 30 degrees centigrades, it was not under my control. That was going to happen, but it was important for me that point B not move. So I decided that in order for me to achieve that goal, I was just going to come to bar AB and apply a temperature change that would cancel the effect of the heating up of bar BC. Now, the question is cast that way just to make it interesting, right? Because now I can translate it to a much simpler one, which is simply what? Find the temperature distribution on bar AB that gives me 0.51 inches upward, because this deflection was downward, right? Because it turned out to be plus, and the one kip load was down. So I have now changed the question to how do I heat bar AB so that I get at C 0.51 inches upwards. If I do that and I have both the distribution of temperatures, point C will not move. Okay? So, I will erase. And now we say, okay, so now I'm interested on AB, right? So how much to heat AB such that delta C in the vertical is 0.51 inches upwards. Okay? So, since I am going to heat bar AB, and I am interested on what happens in C, I of course need to put a 1 kip load here, right? Because that's my goal, always. This is my distance X, and I'm going to use the fact that M1 here is just X. Okay? If I want. Shear is 0. No, shear is not 0, and axial is not 0 either, right? So shear I don't really care because the shear doesn't produce deformations, but there is an axial here, which we calculated before, and that axial was compression, and it was equal to 2 over square root of 5. No, I think it's 1 over square root of 5. Double check. Double check. The axial force yes, is 2 over square root of 5, yeah. Due to the 1 kip, right? So this is the unit. That moment X, it's obviously positive, like this, right? So it's when the moment is producing bending that doesn't hold water. That's positive M1. Now, since we put the 1 kip load down and we want to get 0.51 up, that means that we need to get negative, right? So my loading condition is such that here I have phi from temperature 0 and epsilon from temperature 0, so I don't care what happens there, right? Now here I need to get something from temperature, and here I will get something from temperature also. Now, I should have been more clear with the constraints, but okay. What I'm going to do is to say, if I increase the temperature at the bottom by delta T at the bottom, this is H bar, or 20 inches, right? I'm going to get a phi P due to the temperature, which is going to be minus delta T at the bottom over H bar times alpha, right? Because this is going to be, alpha. These are the strains. So the coefficient of thermal expansion times delta T is my strain divided by H bar is my curvature. So this is the angle. That's the curvature due to temperature. So I have that's the curvature. Now I could have handled it in a more blind way, I guess, and maybe that would have been better from a point of view of instruction, instead of trying to have you follow why I'm putting a negative. But I guess let's complete it this way. If you guys get confused, you can ask and I'll try to clarify. But notice that what I'm saying here is that my one kip load, which I could have pushed up, but I kept it down as before, is doing this, okay? And therefore, we're supposed to get delta C of 0.51 up, so that means delta C1, delta CB should be minus, right? If I keep the one kip load downward. Now actually maybe, you know what, wait a second. No, it's okay, okay. So minus 0.51. This is what we need to get. So, so my curvature is this, and my strain is this. And that strain is, what, how big? It's half of this, right? So it's alpha delta T at the bottom divided by 2. Now is it positive or is it negative? Again, this is the part of the sign that I could have done a better job, but I'm just finishing the way I presented it. Is it positive or is it negative? Well, the N1 is positive compression, if you look at your free body diagram. So we've taken this N1 to be plus when the bar is shrinking. But if I put temperature increase here, this is elongation. So this is opposite in sign to that. So these two negative signs are reflecting the fact that they are in opposite direction as the values here. That's all they mean, right? They don't really mean that they are always negative or that they're negative because this or that. All these negatives say is that curvature is opposite to the way that moment produces curvature. That strain is opposite to the way that axial force produces strain. That's all it's saying. If we reverse the sign convention here, this would be plus. Now that we have those two things, then it's over, right? We just plug it in. So we say delta C in the vertical direction is the integral. From 2h to 4h, I'm using the x, of m1 x times phi p, which is delta temperature at the bottom over h bar, times alpha, times ds, which is what? Square root of 5 over 2 dx, right? With a negative. And that is the bending part, minus the integral from 2h to 4h of the axial contribution. The n1 is 2 over square root of 5, right? And the epsilon p is the minus y. This is minus alpha delta t at the bottom divided by 2. Square root of 5 over 2 dx. When you plug it in, delta C vertical works out to be, after all the substitutions, taking h equal to 10 feet, as we did before, you get 2160 alpha delta t at the bottom plus 120 alpha delta t at the bottom. In other words, these two integrals with a minus, these two parts give these things. And then if you say minus 0.51 is equal to minus the sum of these two things, which is 2280 alpha delta t at the bottom, and you know that alpha is 12 times 10 to the minus 6, you find that delta t at the bottom is equal to 18.8 64 degrees centigrades. So, if we had this structure, this is all we're saying, right? If we had this structure, now I'm drawing it with the size, and this part here was heated by 30 degrees centigrades, so that the temperature distribution across it was like this, then that point would move up a half an inch. No, I'm sorry, that point would move down a half an inch. If we come to this bar then, and we hit the bottom by 18.64 degrees centigrades, then this point doesn't move up or down. It might move horizontally, but it does not move up or down. Actually, it will move horizontally, but it doesn't move up or down. Okay? So that's it. I am going to now go and see how much issue there is in uploading this. We'll be in communication soon.